Morning, everyone. We're very happy to have Professor Chetan Arora from IIT Delhi visit us today. Professor Arora is a professor in the Department of Computer Science and Engineering and a joint faculty in the Yardi School of AI at IIT Delhi. He received a PhD in Computer Science and BTech in Electrical Engineering, both from IIT Delhi in 2012 and 1999, respectively. He did his postdoc work at Hebrew University, Israel, and before joining IIT Delhi, he was a faculty at IIIT Delhi. His research interests are broadly in computer vision and more specifically in trustworthy AI, cancer detection, and mobility. Professor Chetan Arora has published several papers in top computer vision journals and conferences and supervised over 20 PhD students. And he's also founded 3 startups working on computer vision products. So without further ado, I'd like to welcome Professor Arora to give his talk today at KIAC.
In computer science department. In IIT Delhi, we have a mechanism where one can get associated with multiple academic units. So we have recently started School of Artificial Intelligence at IIT Delhi, and I'm also holding a joint position with them. My area of work has already been said, computer vision. And so I did my BTech from IIT Delhi in 99, and my BTP was on vision. So now it's about 25 years since we are doing vision. So I don't know whether many of you have seen that, but even at that time we were developing face recognition model with SVMs and Viola Jones, those kind of stuff. So we had to put a label in the lab, don't touch this machine, because the training used to happen for 3-4 days. So now the world has changed. I'm a faculty now there, and so this is some advertisement about our own lab. This is the kind of work that we do. So the top 3 are more application-oriented things that we do, and the bottom 3 are more ML theory kind of things that we do. So we have over the years started investing a lot into the healthcare, and that's what my talk here will also be on. But when we are not doing healthcare, we have one big interest also in the mobility space, where there is a car, there is a camera, which is looking at the road and what can we do there. Creating 3D maps of the scene, so that's the geometry part of it. We also do lots of object detection, semantic segmentation, depth perception, etc. Through that. We have also in the past worked a lot in wearable cameras. In fact, sometimes I see that in my Google Scholar page, the top cited paper is actually wearable cameras. So we have done a lot of work, but I think that top cited is just because we were perhaps the early movers into that space, so got a lot of citation because of that. We are also interested in, as I said, some theoretical aspects where we talk about how do we make machine learning more reliable. And when I say that, we are talking about confidence calibration, we are talking about OD detection, we are talking about the trustworthy, the adversarial attack perspective. When we are if I talk a little bit more about the theory, so we have also worked a lot in probabilistic graphical models, where we talk about the structured prediction and specifically in the higher order inference, etc. So I'll not talk about a lot of the theoretical work. So we'll focus only on the healthcare. So going quickly into what we have done in the healthcare space. So this is our specific interest in the healthcare space. The top 2 are the cancer detection, gallbladder cancer and breast cancer. This is something that I'll be talking about today, actually. But when we are not doing cancer detection, we also do surgical video analysis. So the aim is eventually at some point, so we collaborate with the neurosurgery department there, that's just like we have the Da Vinci robot for, let's say, the laparoscopic surgery. Can we someday invent in India Da Vinci kind of robot for the brain surgeries? I think that's where the need is. So we're slowly developing the tools with it. And because it's not a full finished end-to-end pipeline at this moment, so we keep on applying whatever tools we develop on the simulators. So we have developed several surgical simulators where we train the doctor to conduct a surgery there. So we have to do this tool and the tool tracking, the tool pose estimation, all those things in a simulated environment. We also work on this, what I call this population level data collection kind of stuff. So these are technology-wise small interventions. But when you are in the healthcare space and when you talk about the population, even the small intervention can actually make a lot of impact. So this is an example of that. So all of you may have seen this. So when a child is administered a vaccination, so the date is mentioned on that immunization card. So everybody forgets about when the immunization was, and we also forget when my child was there, when was the vaccination due, when is the next vaccination has to be done. But we can look back, see that immunization card, and we know when is the next day. But think of it that half of the Indian population may not be literate. So this booklet is of no sense to them. So even if you give them, they don't know that where is the next immunization due. So what we did is then that you take this booklet, but we also ask the A&M or the ASHA worker, whoever is putting the injection, to take an image from a mobile phone and upload to the server. Now, once the image gets uploaded, we have the phone numbers, we have the dates, we have the associated vaccination, etc. So we have the full information about the child's immunization status, and we can make the calls ourselves one day prior to that tomorrow that vaccination is due. So based upon the software that we developed, somebody did, a company actually did a field trial sort of in a district, and we found that the immunization compliance improves 10%. Just by making them, you just have to remind them tomorrow is immunization, and 10% more people can come in. So that's the kind of thing that we do. So now let's go into the little more technical details of what I wanted to talk about. So I'll talk about two primary techniques, gallbladder cancer and breast cancer. And the basic agenda of this presentation is that I want to really show that one is an aspect where we are talking about visual recognition and computer vision. And there is a separate thing which is now the cancer detection, but they are actually together. I mean, I can look at it from the computer vision perspective, and these are really object detection. So doctor would like to say that from a computer vision perspective, I see an image, I see an abnormality which is localized, and I have to put that bounding box somewhere and say this is an abnormality, cancer. So in a natural image, I would have said the same thing for a car or a person. Now I'm trying to say the same thing for the cancer. So visual recognition wise, it's just an object detection. But we have to really understand that how the doctors are looking at the image, what are really the key ideas of their diagnosis, and try to mimic that into our neural networks or ML models. So that's the aspect where I want to really highlight upon how do we really translate clinical knowledge or clinical understanding into what we do into the machine learning. So the first thing that I'm going to focus upon is the gallbladder cancer. So gallbladder cancer, I'm assuming this is mostly a technical audience, so we may not be knowing what even a gallbladder is. So we have the liver, which is the biggest organ in our body, one of the biggest organs in our body. And below the liver is this small balloon-shaped thing, which is called the gallbladder. And whenever we eat the food, so the gallbladder secretes some juices into the liver, which helps in the digestion of the fat, etc. Because the liver is sort of authorized or is the main component for all kinds of digestion, so if something happens into the gallbladder, it will quickly go into the liver and then to the whole body. So the 5-year survival rate is very, very low, 5%. So the people who will be diagnosed will not survive beyond 5 years. So let's say 95 of them will not survive. Mean survival is also 6 months. So it's very scary that you diagnose and within 6 months, the diagnosis becomes very poor. And we have 84,000 deaths every year just with this. And the thing is that the gallbladder is just secreting some juice and helping you digest. So most of the time, you won't even realize that something is wrong. At best, what you can have is some abdominal pain. Many times that also won't happen. But if there is some cancer, then as I said, it will go through very quickly to the liver and through the whole body. So that's a problem. So these are the kind of images that one would see. So this black portion inside is the gallbladder, which we are, and then we are looking, so that sometimes you have a gallstone, sometimes the boundary is blurred. So that if the boundary is blurred, that's the biggest sign that there is something wrong. Otherwise, there should be very clear boundary between the gallbladder and the liver. If the boundary is missing, something wrong has already happened. So within these, we have to sort of detect whether the person has a gallbladder cancer or not. Now, why is gallbladder cancer such a big issue? So typically, let's say when we talk about the chest X-ray, when I talk about, so we also work on the breast cancer, the mammograms, the images that we see there are very structured. Okay, so let's say if you're looking at an X-ray, somebody will make you stand in front of the sensor, then the P and AP view, front and back. So every time you get exactly the same view of the lungs. Okay, slightly here and there, but mostly the same thing. On the other hand, The ultrasound modality by modality is a handheld sensor. So you have a sensor and I'm putting it on your abdomen. So my abdomen may have a different structure. Somebody is fat, somebody is thin. The doctors have their own way of holding the sensor. Somebody will hold it like this, somebody will hold it like this, because of which the view that I'm getting is very different. Okay, and so think of it that I have a 3D structure and I'm cutting a plane into this 3D structure, and that's the view that I'm seeing. So even if you have slight change in this orientation, suddenly the view will change. Okay, so it's a handheld sensor that itself adds a lot of problems from the automated analysis perspective. And then it's an ultrasound, which is an audio-based sensor. It has a lot of noise, so you can see the image typically will not be very clean and will have a lot of artifacts. So for example, the biggest structure that you see in this image is of this black portion. Okay, that's the biggest, most prominent structure in this image. And this is actually no structure. It's just an artifact because there is a stone on top of it. So the ultrasound wave that is going here does not reach here. So the biggest structure that you see in this image is actually not a structure. Okay, just an artifact. So there's a lot of noise, there's a lot of artifacts because of shadow, some spurious texture which will keep coming in there, and handheld sensor. Overall, things become quite problematic to analyze. And then we have the anatomical stuff, as I said. So it's a largest tissue, and there's a balloon-like structure which is go on inside. And what I will get is lots of very low intra-class variability. So I have class A, let's say cancer, I have class B, which is not cancer. There'll often be very little difference between the two. It's just a small boundary between the liver and gallbladder which has gone missing. Otherwise, all look same. On the other hand, there will be lots of intra-class variance because of this view variation. So the gallbladder is all benign or malignant, but because I have held the sensor in different way, I'll get very different views. So very high intra-class variance, very low intra-class variance, and I don't have the data sets. So the problem becomes very difficult. So within very small data set, and you have to handle all these challenges and make it work. So when we started working on this, these were the questions that we asked. So the first question is obvious, that how can I really handle these challenges of the visual recognition and make the detection work? But we are also aware that this is a medical imaging problem. So the doctor is not happy just listening from an AI model that this is cancer and this is not cancer. Okay, because ultimately the doctor has to tell to the patient that you have a cancer because of X. What is that X? So the idea was that we will be aiding the doctor. Okay, so the doctor is looking at the ultrasound. He may have missed the cancer. AI model comes in picture and say, hey, look at it, looks like something abnormal. Why don't you look it carefully? That was the mode that we wish to work in. But now if I say, hey, look at this is some abnormality, where is the abnormality in the image? So I have to give some kind of an interpretability, the interpretability which the doctor can understand and then can accordingly communicate to the patient that you may have a cancer because of reason A. And we have to do it all under very limited supervision. I have to keep the model reliable, and I have to also see that this is bias free. Okay, so now you can understand that many of the theoretical work that we do become applied in the application work that we start with. So the gallbladder, unfortunately, is a very India-specific disease. Okay, even in India, I think the South is saved from it. So it's mostly a North and Eastern Indian disease. So you can call it the Gangetic belt disease. Sorry? I mean, that's not, the factors are not known, but so for example, BHU is one of the biggest receiver of the GBC patient. The PGI Chandigarh is one of the biggest receiver of the GBC patient. Similarly, in the Northeast, it's not there in the South and West. So it's an India-specific disease. I think outside India, it's prominent are Japan and Chile. Again, no much US into the picture, no Europe into the picture for this. So we have the highest patient load, but because let's say Europe and North America are not involved, so there is almost no work that has been done in this context. And when we started, we were the first one, then we released the data. Now it looks like that there are other groups also working on it. But we were the first movers into this. So the first thing that we created was create a data set. So we started with this, we created a data set. And this was the first data set. So this is the scale that we have to work with. So we had 218 patient data. Okay, and typically it's an ultrasound, so I can take multiple views of the same patient. So in terms of the images, I had 1255. That's the whole data set I have. So within this, I have to train and test. And within this also, there is going to be class imbalance. So there were 265 which were malignant samples and 990 they were benign samples. So whenever I say malignant, so there could be bias from the radiologist. So the radiologist may or may not have picked or may have said false positive. So any patient which has been said that it is positive is biopsy proven. Okay, the reverse cannot hold true for the negative, because if the doctor thinks that the patient does not have a cancer, unfortunately we cannot confirm through the biopsy that it does not have. So it's one way confirmed, the other way is not confirmed. So that's the background. Now let's see how I can detect the accurate GBC detectors. Okay, so I have to detect a gallbladder cancer. This is the only data set that I have got, and I have to detect the accurate one. So we did that work, and so I'm talking about 2022. So the first thing that we realized is that computer vision perspective, this is actually an image classification problem. So I take an image and I say cancer, not cancer. Or if I'm a little more, want to be more accurate, so I can say cancer, there is a benign abnormality and there is a normal. So I can make it a 3-class or I can make it a 2-class. Okay, but it's a classification problem. But unfortunately, even if it's a classification problem, formulating it as a classification is a bad idea. Why? Because I have just got 1200 images. Between them, I have to also do this 2080 or some kind of a train test split. So in this 1000 images or 800 images, if I say that this is an image classification problem and lots of low inter-class variance and large intra-class variance, the model just even don't know what to look at. Forget about the robust classification. So we said that even if it is not a classification problem, let's make it a detection problem. So we pose it as a detection problem and we say, first the model should be able to detect where the gallbladder is, then worry about whether it's cancer or not cancer. So we created this ROI based stuff. So at that time, the faster RCNN was easy thing to do. So you pass it through the faster RCNN and get the ROIs. So I'm not calling it gallbladder because all I am interested in is that you should not look at the whole image and say classification yes, no, focus on certain region. That region should be gallbladder, but at the test time, even if there are 2 regions come out, I'm okay to actually pass both the regions and say classification. Even if one of them says positive, I'll say positive. Okay, so it's not very hardcore object detection there, but I just want to sort of focus on the right region. So now you can, in the retrospect, what you can say is that I'm trying to attend to a certain region, although at that point we did not apply the transformers there, so it was all CNN model. So once a regions have been identified, okay, although the gallbladder is only one in that image, but ROI wise, I can have multiple ROIs from it. I will pass them through the classifier, and then even if one of them says malignant, I'll declare malignant. If all of them says benign, I'll say benign. Okay, so that's how we got the model done. But even this was not working. Okay, so it worked to a certain extent, it worked better than the state of the art, but it was still not satisfactory, the performance. And the bigger problem there was not necessarily the region itself, but also the ultrasound modality. Because as I said, the ultrasound modality has a lot of noise in the image. So I have to somehow handle that. And this is important because maybe with the noise also, if I had 1 million images, I would have said. But because I have 1000 images and that to noises, the model is just not able to concentrate even if I give an ROI. So we relied upon something else. So there is a separate work which is going on at this moment in MIT, and I happened to listen to the lecture. So in MIT, so they are working on how does the vision work in a human. So when a baby is born, the vision is very bad. Okay, so the baby sees very blurred images, something of these kind. Okay, but the brain has developed. So the vision is developing for the first year, but the brain is started to make sense of the visual input that is coming to it. So the first visual input that a brain has to start understanding is of this kind. Then over a period, the vision improves and the brain starts looking at these kind of images. So which means that the brain, the natural progression of the brain is in such a manner that you first see the blurred image and then you see the high-res image. So they did a very interesting study. I mean, it's actually happening in collaboration with IIT Delhi. That's how I came to know about it. So there are some, let's say, children who are blind from the birth, but their vision can be corrected. Now, so they identify such children whose vision can be corrected, and they actually pay for it and they get their vision corrected. But in the process, they get a very useful test set, because you cannot ask a 6 months old baby how he is looking at the image, but you can definitely ask this question to a 10-year-old child. So the person is blind from the birth. At 10 years, the eyesight has been restored, and he or she is looking at the word for the first time and explaining how he's looking at it. And they did lots of experiment on top of it, and they found out that if you restore the vision, then the person, I mean, if you show them the two persons in a natural view and let's say smiling, the person will understand them as two different identities. So what they do in their experiment is that when they restore the vision, for some time, they artificially give them the glasses so that you look at the blurred vision. Because you have to sort of, the brain has to start understanding the image in exactly the same fashion. The blurred followed by the high texture. Okay, and now think of it, this is very important from the neural network perspective also, the artificial neural networks that we are training. So we give the high resolution image to the artificial neural network, and the neural network never gets a chance to look at the contour. It always looks at the high frequency features, if I talk about the image frequencies. And this is also a problem now, what we are seeing in the context of the ultrasound images that we are seeing. So I am trying to train a model. I have only 800 images to train with. And my model is somehow worried about this small speckle noise that is coming into the picture. It's not able to focus where the gallbladder is, where the boundary is missing or not. So how do I train it for? Well, say, okay, let's blur the image. Okay, now I would like to highlight that this blurring is also a data augmentation that one does. Okay, but this is not the data augmentation that we are talking about. So because if I were to talk about data augmentation in one batch, I'll put some high-res image, I'll put some blurry image, or I'll put some other noisy images also. So here I'm talking about a curriculum. So the first 30% of the epochs will all be with the blurred image. Maybe the accuracy will be less, be it, but it will all be with the blurred image. Then the next 30% epoch, I'll reduce the blur. I will also keep the older blur and the newer blur, because the brain has, or the artificial neural network has already started to understand the blurry image. I'm adding now the information into it. And then in the next 30% or last 40%, I'll just let it be the full. Because I'm trying to mimic how the brain, the human brain got developed. So that's my style of mimicking that process. And in that process, what happens is that because in the first 30% of the epochs, I'm asking my neural network to tell me whether it's cancer or not cancer, whereas the only thing that it sees is the gallbladder wall. Remember, so all this speckle noise has gone the moment I blur. So it has to actually force itself to look at the edges and not the speckle noise, because that's the only information that is there in the image. And over a period, I'll keep on adding the information, and the model will get trained and will get trained in a manner which is robust, which is not actually focusing on the speckle noise, but is looking at the structures in that gallbladder and liver. So that's what we did. So implementation wise, quite straightforward. So I will start with a high blurred image where you can only see the structures, nothing else. And over a period of time, I'll keep on reducing the blur. And finally, the final epochs that will run will happen with actually the original image. Okay. Sorry? Scale space. Yeah. But the scale space in a curriculum style. So we did some experiments. So I took this image and we added this artificial texture into it. Okay. So we are careful in adding this texture in a non-gallbladder region. So this is my gallbladder and this is some texture that I added. And what we saw was that if I train particular models, so this is GBCNet, which is without any curriculum training, and the model starts focusing on this texture that I have added. And if I add this curriculum, the model actually starts ignoring it and still focus on the right things. Okay, just the change in the curriculum. And of course, changes prediction also, because this texture that I've added is an artificial texture. It has no consequence on the answer. So this was the experiment that we did. So we asked the two radiologists in PGI. So this is in collaboration with PGI. So we asked our collaborators. So we gave them 100 images. We had the ground truth already, benign and malignant. and we'll tell them, okay, you tell me which is benign and which. So this is our way of getting the human accuracy. Okay, so this is 3-class accuracy. This is 2-class accuracy. So 3-class accuracy, I said malignant, benign, and normal. 2-class accuracy is malignant and non-malignant. Okay, so this is the accuracy that you get. I mean, in the medical, we are also worried about the specificity and the sensitivity. The sensitivity in our parlance will be called the recall. Yeah. So how many positive cancers I'm able to pick up, and what you see is that is a quite alarming thing. So the sensitivity is at 70-73 for the 2 radiologists. So if I give them 100 cancers, they're likely to miss 30. Okay, and it's a very important statement. And this is the tertiary care hospital when the radiologists know that they are looking for gallbladder cancer. Okay, now imagine a radiologist in some rural remote area, not so expert, unsuspecting, you just went to the radiologist with some abdominal pain. So he's looking for something else, not necessarily gallbladder cancer. But the gallbladder cancer is there. What is the likelihood of the radiologist missing that kind of a cancer? So the ultrasound is also getting done, still you are missing it. There are symptoms, you went to the radiologist, and yet the radiologist misses it. And as I said, the difference between a successful operation and the unsuccessful operation is 6 months here. That's the mean survival rate. So if you went there with abdominal pain and it was not picked and you spend 3 months thinking about the next scan, it's done. So I had to pick it just at that time when you had the first, that was my only chance. Because if it is detected, the things are very easy. I'll just remove the gallbladder. But I have to detect it at the right time. So the only consequence the people will face is that, okay, your fat absorption or the fat digestion will slightly suffer, but you will survive. So, and if you put the GBC net, so these last 2 rows are what we did, and you see that the sensitivity is actually 97. Okay, if I don't apply the curriculum, the sensitivity is 92. If I apply the curriculum, that blur curriculum that I told you about, it's 97. Okay, so there are certain advantages that I get by focusing on the ROIs and not making it a classification problem. So if you look at it, there are many VGG, ResNet, etc. These are classification problems. We also test with the object detection. Even if I give them the object detection, I have to train, I have to put an architecture in such a manner which can look at the textures. So there's a certain other advantage I'll get if I make that an object detection problem. But if I apply the visual acuity, which is this blur curriculum, then I get the maximum benefit. Okay, so again, so we are looking at the image, but we are also aware about what are the characteristics of that problem and trying to translate that into the architecture that we are developing. And that's how we get the accuracy. Okay, so this is, for example, some of the qualitative analysis. And where we are bothered about is many times the networks will just even don't know where to focus on. Okay, these are all red cams where the network is focusing on for the result. And this is where you see for the GBC net. So it first allows it to focus on the right thing and then make a prediction. So you are making the right prediction, but also due to right reasons. So that was our first work in this sort of space. But as I said, that doctors are not happy with only this.
So for visual acuity, did you also check whether it improves the performance for the other architectures that you mentioned, and not just GBC net? And also one thing I was trying to think was, like you trained it initially with blurry images, but convolution architectures generally face this cadastral forgetting. Wouldn't that have an issue that the model will start forgetting these boundaries that it is learning?
So we are getting distracted, but I'll try to give a very quick answer. So there is something called brain plasticity, and this is right now a big debate in the academic circle. I mean, so we are not party to it because we are just the users of that. But so there has been a paper in the NeurIPS which says that if I do it in this manner, the blur and this, then my accuracy will drop. Then there's a counter paper on it also that it drops on this particular data set, but the generalization improves. Okay, so this fact that the blur, what is good. So my understanding is that, I mean, this is my perspective onto it because I don't want to get dragged into the visual acuity thing. So my perspective is that the visual acuity allows me to focus on the structures rather than the textures. And in the case of the ultrasound, it's a very important thing that I do not want to sort of become defocused into whatever the speckle noise is saying me. Just focus on where the gallbladder is the boundary visible, what is the thickness of the boundary, etc. So it becomes very important that I have some kind of the curriculum which allows me to focus on the structure. So that's why it is helping us. Typically in the research, we are not fair to our competitors. So we have not done the testing with the others that if I do the testing there, maybe their accuracy also improves 0.5%, 1% somewhere there. But so we do ablation on ours that I will do GBC net without curriculum, with curriculum, classification, detection. But that benefit we do not give to our competitors. So I don't know what ResNet will perform if it were to do like that.
Working with different status, it's happening in both the detection and
detection need not be, because I'm just trying to find an ROI. I don't want to see, because when you took the ultrasound, the prominent features typically are the shadows, which is non-gallbladder, or the fat, which is just on the top. So you see that rings on the top. So you want that, okay, ignore these textures, focus on the gallbladder. So if the detection happens, you are fine. But as I said, I'm not bothered that if the detection is 1 or 3. If it is 3, I'll just give all 3. So we've developed a new model. We said, okay, we'll try to make it interpretable, but I have to start from the scratch because now I have to make the model bottoms up in an interpretable fashion. Okay, so I do not want to go into this popular style that I'll have another neural network which also give the output as a text. And okay, I'm doing this because if it's hallucinating, it will hallucinate the text also. So we developed a different architecture there. By this time, we knew that localization is important, but we need not have an explicit detection stage. So we build this overall end-to-end pipeline where we say that we take an image, focus on a certain region where the abnormality is, then you crop this part and give it local input and then try to classify. Okay, but it's not now 2 seconds. So it's like a single stage object detector. You can look at it that. But now what we did was we said that this thing, these features will combine and my classification will happen through what we'll call the visual words. Okay, so this is something that I'm forcing upon my model because I want interpretability. Okay, so some of you who may not know the visual words. So in the computer vision, one of the classical way of doing things is that I detect some kind of a words. So just like in the for the face detection, I can say, is the nose present, is an eye present, is an ear present, and if some of these visual words are present, then I'll say the face is present. So my image is really a bag of words, just like a document is a bag of words. So that's a bag of words model. But interestingly, what it tells me is that it's interpretable. I have said this as a face because nose and eyes were present. I have said this as not face because ears were not present. So I can actually argue about the presence or absence of a certain word, and then I can reason my decision with it. So that's what we said. We said that, okay, we will force my model to be on the basis of the visual word. But how will I get the visual words? So the visual word for me is the feature maps that I got. Okay, so remember in a neural network, at some point I'll get some H by W by C tensor. So I'll say each of this plane, each of this channel is like a visual word to me. Okay, and if I get a high value in some channel, this is my visual word present in that image. And the location of the channel will tell me where that visual word is present. So I'll interpret these channels as visual words. And then I'll just say, I'll do this max over individual channels. So I'll get presence and absence of a word. And then I'll just use this vector to do the classification. So I will force my architecture to behave like this because I want interpretability. But how do I know that which channel is which word? That's also easy, because what I'll do is I'll ask the doctor to write the report. So I have an image and I have certain description that the doctors gave. That's my training. And all I have to do is now mix and match. So I say the doctor said loss of wall, and these 3 words, these 3 channels were activated. So now I have my mapping that these 3 channels represents these 3 words. I can do that at the train time. I don't require a lot of data. It's like even if you give me 700 reports correspond to 700 sample, I'll say which words were present in the report, which channels were activated here, and I can make this match. Once I make this match, at the test time, I can just look at which words were triggered, and I can accordingly create my report that I am giving it positive because of this reason. That's what we did. So this is now the outputs. So I know that the feature number 1321 is activated, and I know that the feature number 1321 is associated with loss of interface between liver and GB. So I can tell the doctor now that I see this image as malignant because I'm not seeing the boundary between the liver and GB. And the doctor is also happy, and I have an interpretable decision making in 800 samples. Not trying to do anything fancy. Okay, so we did this also, we published this paper also. But we were still struggling with this fact that I have about 1200 images across 300 patients. And then we realized that these images are not the direct thing that I get. The first thing that doctor gets is a video. Okay, so you scan this and you get a video, and the doctor selects an image for me, through which I do. So we ask this question, can I make use of this video? So that's the next step. So I have some unlabeled videos. Okay, so I don't know what frame the doctor captured. I have no way of asking my radiologist that you annotate each and every frame for GB or for the classification. Say, okay, give me those videos. And just like the trend these days is, can I do this unsupervised training with that? Okay, so I will use this video for pre-training my model. And what's the thing that I can do? So I'll say that this is frame number T. Frame number T plus 1 cannot go too far from it. Okay, seeing almost the same stuff, slightly the different view, or maybe slightly shifted. So I'll say that this and this feature is a simple contrastive learning. This and this feature should be identical because these are just temporally adjacent frames. And as you go far from in the temporal, the feature should be different. So we did that, and then we did a little more into the contrastive learning. So we have different patient data. So I'll say one patient and the other patient should always have different feature. One patient within the same video and some, let's say, time margin will have the same feature, and then the other will have different feature. So we also created sort of a curriculum over the contrastive learning. How I will, at what point I'll say that these two features, these two frames should be same feature, these two frames should be large. Yeah. We did that, and it reaped benefit.
There's like,
yeah,
the doctor scans actually. Even like a periodical interval,
right? The same location you come back and
yeah,
go.
can
Right?
come back.
So if you are treating that as a negative one, then you are going to have a bad effect of learning there.
Right. So, but in this case, let's treat that as a pseudo level. And if I'm okay 99% of the time, 1% time, if it still happens to be exactly at the same place, the model is able to take that much of a noise. I think that's what we these days do in any just large scale.
But I am also worried about you are looking at the same structure, right? At a different variation, because the one video is coming from the same patient, same organ. Is it okay? Are you going to use the samples away from the current sample as a negative?
Yes. So the different patient will all, I mean, at least in the initial epochs, will be treated as different features. Same patient, temporally adjacent, will be treated as the same feature.
Okay.
Away will be treated as different feature. But there, what you are saying could be a problem that I could have rolled back to the same loop.
Exactly.
And I may have said this negative, whereas it should have been positive.
I have some more problem on this because we are looking at the same organ for the same patient.
Yes.
But there itself we have a conflict. One time you are saying they are positive to me, the other time it is negative, right? So it works for the images because they are all taken at different instances of this. For example, the same class objects, you treat them, they are different at least from the object sense. But this is the same object that we are saying again negative, right? So that is where we have issues. Probably you should have avoided that video and then taken something.
See, the whole purpose of bringing in the video was that I want to do some kind of a pre-training without necessarily involving the doctors. Because if I ask the doctor, I have got 1200 minutes to work with this.
That is perfectly
So
fine.
you're trying to increase your base. So you say, okay, give me 60 videos. I have some data to pre-train.
Okay, now what I suggest is, can we take that video as a positive, any frame, okay, and all other videos negative? I have no issues in that.
So we can do that, but in any case, we have graduated from there also.
Okay.
So I'll tell you that. So we did this video-based pre-training. I agree with what Venkatesh is saying, that there is some problem in terms of the pseudo labor at times. Although my personal understanding that it doesn't happen too often, but it can happen theoretically. And what we see is that suddenly the accuracy improves. Okay, just with this pre-training, I mean, just with any other pre-training. And for the paper, we also showed that it's not necessarily the GBC specific, because this fact that I can do this video-based pre-training and then do followed by this fine-tuning on my data set, I could have tried it on other things also. So in that case, we have some video-based data for the COVID also. So we tried there also. So this video, so ultrasound video pre-training actually helps. So I take my GBC videos, train the model that this ultrasound and this ultrasound is same, this ultrasound and that ultrasound is different, and take this pre-trained model and fine-tune it on the COVID. Okay, so the COVID is lungs. Yet this pre-training helps in that context. Also, the model has really learned how to look at the ultrasound images in some manner. That's what is happening. So we did that. So it happened. But when we did this work, we realized how big a fool we were. Okay. So we have been, so understand that we started working in this 2021 kind of stuff, and 2-3 years have elapsed. And the accuracy is not beyond 90% or something, because the bottleneck is now not at the EI end, but at the radiologist end. Okay, so the radiologist is scanning. He does not suspect there is any cancer. So what is the view that you are going to get? Some arbitrary view. So whereas the label is of a patient, the patient is positive. That's what I know from the biopsy. The view is biased by the radiologist. The radiologist selects the view, and if he's not suspecting, you get a bad view. So now if I talk about this as a chain, the weakest link in the chain has moved from the detection to the capture. And we are saying that this is in front of us all the time. That the radiologist always says that the label is patient. Patient A is positive. All the views in it is positive. Maybe actually some views were not really positive. The radiologists think that this is positive indication. So if I were to really correct it, I should have from the beginning started working with a video-based label. So it's actually not even an image classification problem. It's actually a video classification problem. So I have an ultrasound video. I know that that video is positive. There is no way of knowing that this frame is positive. Whoever is telling is a radiologist, and he or she may have his or her own biases into it. But this is 2023, and we now know foundation models and video foundation model, this and that. So we have, let's say, the technology base to really work with the videos in the small amount of video data sets. So we did that. And so this is MAE training, which typically happens. Okay, so masked auto encoding. So you take a video, you hide some parts of it, and then you ask the model to regenerate that part. And through this process, the model learns what are the right features for that particular. So we did that also. All we had to do was just make the small change, which we already know that is very important, that whenever you do anything in the medical images, don't assume that the model will automatically learn. You have to sort of guide and nudge the model to the right place. In this case, what is the right place? Gallbladder. Okay, so if you give me a video, 100 videos, and say mask auto encoding, and the model will learn the features, it will not. First, tell that do the masking only on the gallbladder. I'm not bothered about the fat layer. Okay, so that's what we did. So we call it Focus MAE. All we do is that we take an MAE pipeline, and we just say where I want to mask the things. Okay, so there's some more detail into it, how I find the masking, the tube, and the other stuff that you can look at in the paper. But all I'm trying to say is do the mask in a proper manner where there is gallbladder, where I'm likely to see the problem. And you put that into this whole pipeline, which is basically an MAE pipeline, and you get your focus MAE, which is focusing on the region of interest and then doing the masking. And what we got with this video-based classification was that we actually bypassed all our stuff. So this GBCnet is also ours and that format is also ours. So at the time we published the paper, that format was slightly better than GBCnet. Okay, so the GBCnet, this RAD format is just visual word-based model that I showed you. And these are all MAE papers. If you are not careful on sort of focusing on the right region, then you can not get beyond a certain value. If you do this focus MAE, then everywhere the numbers will start to improve. Interestingly, for the first time, we got the sensitivity, which was 1. I mean, I'm not saying that we have perfected the art, but on the data set that we had got, we could pick up every gallbladder cancer that there was. Okay, because now I'm not limited by what the radiologist thinks. If the radiologist is not thinking cancer, he's not going to give me the right image. So I have to work with the whole image, whole video. Okay, so now these are the kind of videos that we work with.
Say the photo you're showing.
Right. Okay, so now this is benign video. So now I'll take this whole video and then predict for the whole video. And these are some of the malignant cases. Okay, so the radiologists don't have to suspect anything. You give me the whole video, malignant or benign, don't bother. I will look at it. Okay. And so these are some of the work that we are currently doing. So we have actually made a web app and IoT device for installing all of these things. We are now trying to look at, so this was still video-based classification, the focus MA stuff. I believe that there is a case for video-based detection also. That's what we are trying to work on. The biggest problem now that has become for us is the way we start doing the transformation, this translation. So we installed it on the PGI, we installed it in the BHU. Now, the bigger problem that has happened is this domain shift which is happening. So one radiologist hold it in different way, the other radiologist will give it in different way. In terms of machine learning, this is a domain shift problem. What about the machine will also create problem. So even if I have good detection in the PGI, how can I make the good detection in the BHU? Is what has also become important. We have also now diversified into the CT-based detection where we are not talking about the management protocol. So you have detected a CT, but the management decides upon a particular presence or absence of a gene. Can we really detect that gene? So that's also we are trying. So this is called the radiomics in the medical world. But from the vision perspective, it's really a classification problem. Take an image and tell me HER2/neu is present or absent. So these are the web interface that I was talking about. So we have this web interface which is working in IISc server. So a doctor can upload the image. What we force the doctor is to tell me his or her own prediction, because I want to see it as an assistive device and not an autonomous device. Okay, so it's not going to detect on its own and say ki kar lo. So the doctor has to tell what he or she thinks. Then I assist and say, okay, I think here and here is abnormality. Why don't you look at it? Ground truth may or may not be available. That's not mandatory, but your prediction is mandatory. And then you can choose which model you want to run, because now we have a bouquet of models that one can run on.
Right, so we pick up something with it.
So this is doctor uploading. So we have a tick somewhere that can we keep this image or not keep this image. So based upon the tick. Sorry. So so the video is just 3 months old model. So it's not yet there in the public domain. So it's on the GitHub, but it's not integrated with the demo things. And then you can get normal benign and it gets the confidence, etc. You get the. So we also ported this onto a device because the doctors are not tech savvy. So you have to give them something which just works. So this is a small Jetson. And so what now happens is that, so all these medical devices are already sort of pre-programmed to push the data into a hospital database. So this protocol is called a PACS. So the machine can already talk to the PACS and send the data. So all we have to do is we have to say that there are 2 PACS servers now, PACS server A, which is the hospital. There is a PACS server B, which is actually this Jetson. And so the interface is that there is an ultrasound machine, there is a monitor, there is another monitor, which is a small Jetson below it. So the doctor takes the video and the image, says push to the PACS, the Jetson gets it, and immediately in the next you get what we think about the AI. So it's like everything real time online and all through this device. So the Jetson these days is about 50,000 rupees. So we're giving this 50,000 rupees device. You do the GBC detection anywhere you want. No internet required, no privacy stuff. Everything stays in there and you can do the detection. Do I have time for the breast cancer or we just skip? Okay, so so we have done some similar work for the breast cancer also. So where we talk about what is the clinical insight, how do we really make the model accordingly. So I'll skip that and I'll just show this result. So now we have the models which have the negative predictive value, which is actually better than the commercial models, and they are free to use. So in our pitch, I actually use two words for the AI. One is upscaling and the other is upskilling. So the upscaling part is that where the radiologist is not present, can I really triage the patient using the AI and send it to for the screening? So this is the upscaling part. So I can triage many more patients and then say that, okay, you should go to the doctor. The other is the upskilling part. If I can improve the accuracy of the medical professional who's already there. So this is some experiment that we did at AIIMS. So we have the consultant, we have an SR, we have an MBBS doctor, we have a technician. We ask all of them to do the breast cancer detection. And the accuracy curve is like this, which is understandable. Accuracy, the sensitivity for a consultant is very high and it falls as the skill level goes down. The interesting thing is that if I give an AI-based nudge, that, okay, hey, I'm looking at an abnormality here, why don't you look at it again? Then everybody's sensitivity improves. Okay, and the sensitivity is now almost equal to the consultant without AI. But the thing is that the consultant accuracy also moves up with the AI and the consultant moves to a higher level. So there are some cases which an AI is able to pick up, which these guys are not able to pick up. But there are definitely some cases which AI is not able to pick up, but consultant is still able to pick up. Okay, so that's the status where we are in, and this is what I call the upscaling, because I can enhance the utility of all these guys and make them equal to the consultant. So if you, in a remote area, if you don't have a radiologist, even if you have an MBBS doctor, give him AI nudge and the things will improve. And these are some of the videos for us. So now all of these are installed. So we have these kind of devices now, the Jetsons, which can do mammograms, which can do gallbladder, some other videos, sure, too. Which can also do the chest X-ray, etc. So all of them are integrated in the single device. So because the benefit with the Jetson also is that it can load models, but it can load many models. It's like an iPhone now, and these are apps. So I have an iPhone, which is this Jetson, and I have the capability to install my apps into this, and I can keep on installing more and more. So I can install breast cancer, I can install GBC, I can install chest, and in the future, whatever else will develop can also work. And we already made the deployments also in 3 places, and these are dashboards from there. So for example, in AIIMS, we have already looked at 804 samples, some benign, some positive. In NCI also 604 samples. PGI is a new addition there. I mean, so they are slightly away from us. So these are both in Delhi, so it's easier for us to really maintain them. So PGI also came really, but they have also started using them. So that's the status right now for various installation, and I'll end my talk here. Thank you.
So you mentioned about the visual words for gallbladder detection or problem detection. So how would you actually get those visual words for you?
So visual word, we did it for the gallbladder cancer, but I would say this is for general explainability in the medical images scenario. I mean, tomorrow I can do perhaps the same thing for the mammogram also. So in the gallbladder, there are certain reasons that the radiologist will typically give to. So this is called GB RADS in the medical language. So reason A, B, C, D, and because of that reason, they have already agreed upon a certain protocol that if this feature is present, then you should say severe cancer or early cancer or something like this, and that's what they have agreed. That's what they call the GB RADS. Our purpose in this case was that, can I really tell for my prediction what GB RADS it would be?
Okay.
So first we had to change the architecture, because if I just train the model in the normal manner, I have no access to what should I say. So I said that, okay, let's change the architecture in such a manner that my classification will happen only upon the basis of the words. So I said that whatever my tensor is, last tensor based upon which I do the same, I'll do this max pooling. I'll see individual channel as a word. So I have the presence or absence of a word. Because I'm doing the classification, I'm not bothered about where that word is present. I just say the word is present because my local and global branch are already doing the localization. So I'm not bothered about that. So I say that, okay, let's say I have 1024. So it's like 2 to 4 by 2 to 4 by 1024. That's my tensor side. So this 1024 now becomes my words. So I'll do this max pooling. I'll get a 1024 dimensional vector and then I'll do the classification based upon that. So at the test time, when I'll get, I know which of these words were activated so that the classification was positive. So these are visual words. The only thing that I don't have now is that this visual word corresponding to what text. It's definitely playing some role. That's why I'm saying classification. But what should I say to the doctor? So I say on the trained data set, I'll do exactly the same thing. But I'll say, okay, in this sample, you said loss of wall, you said this, and I saw that this feature was activated. So I'll associate this text with this channel, or this word. So I have this mapping on the train set, and then when I test set, I'll see what activation, and I'll spit out that corresponding sentence. So that's how we have done.
Thank you.
Just a real question on that. So how do you associate the provisions with text or the channel number, let's say? So do you actually do that matching? Yeah. So how do you do that during training time? Do you actually ask the clinician to guide you?
No. So the clinician just tells me these three features.
Okay.
I see my set. And now my problem is that this text is associated with this feature. And I have this, see, for example, in the first image, I saw 5 activation and 3 words. In the next image, I got another 3 activations and another 2 words. So I have to do this global matching on the basis of this, that this activation is mapped to this word now.
I see. So is there a way to also maybe tell the clinicians to give importances? Let's say, they have 3-4 different, what should I say? Like, textual description or things like that. So then would it be easier or better in a way to train your model if you already know that, okay, I need to find this, depending on your confidence on your channels, right? So,
could have been done this way. But my personal experience working with the doctors is that they themselves don't know.
Okay.
Okay, see, I told you that the accuracy for them also is 70%.
Correct, yeah.
So even if they say ki this word is this, etc., so I will take it with a pinch of salt. So to me, that let's treat that there is some noise in this labeling process. So they have said these 3 words, but maybe this 3rd word was actually not present. So it's like that there is a loss of wall. At what point you say loss of wall? Maybe the wall has thinned, but somebody says loss of wall, somebody says the wall is present. So there is some noise into this words process also. So I have got the labels that these 3 words are present, maybe only 2 words are present, or maybe 4th one is also present.
Right.
So when I do this global optimization, I'm actually a little more robust toward these nuisances. Okay. The global optimization.
Yeah. Just final question. So this, last work or in the previous, the video-based work. So there, the predictions. So are these in 3D or are these in 2D? So the masking is in 3D or masking?
Masking is in 3D. So
masking is in 3D.
In the video classification, the masking is in 3D.
Okay.
Although, so there are some degrees of freedom there also that when I mask, so I mask a full tube or I mask the object tube. So there are some degrees of freedom and we do it in a certain manner. I did not want to distract it from there.
Okay.
But the question was that the main idea was that I should mask only the GB region.
Right.
I don't care how you reconstruct the fat layer. I don't care how you reconstruct the shadow.
Right.
Focus around GB.
Okay. Thanks.
In the first paper which you published, you mentioned about the model was not able to directly identify from the high dimensional ultrasound images, because of which your team introduced an artificial blurring kind of a thing, like a Gaussian blur. So my question was, instead of introducing the blur artificially, can we not use architecture like UNet, for example, like which downsamples the image as well as upsamples it to actually learn the features?
So UNet is a scale-based stuff. I mean, I'm sure some kind of an architecture may have worked there also.
Right.
But in the UNet also the problem would have been, I mean, although we have not done it, I'm just thinking loud. The problem would have been that the first decision that is being made is being made based upon the high frequency.
Right. Okay.
That's what I wish to stop.
Okay. Right.
Because high frequency, see, let's talk about the first epoch. The model has not yet learned what it is. You give me high frequency feature and lots of high frequency feature, and you give me few low frequency features. And you say, okay, I'll combine them and then predict. These high frequency will dominate.
Okay. Right.
So I want to actually kill high frequency, at least in the first few epochs. So the model is forced to learn the shape and the boundaries,
Contours
and
and
of
stuff.
things, and then come to the high frequency.
Just to nullify the bias that it has on the high frequency parts. Is that right?
Yes. See, because if I do not do anything, the high frequency part, it gets biased towards.
Right. Right.
And our motivation of doing was that, I mean, our brain perhaps is also not wired that way.
Right. Thank you, sir.
The label comes from the biopsy results.
Yes.
So probably the patient have already had some noticeable symptoms, and they have a clear-cut thing that they have a cancer. So how does the developed model behave at some patient data, like which is taken at an early stage? Because this is a very important thing, because it's a gallbladder. Once it has metastasis to liver, it's out of our hand probably.
Right. So in the case of gallbladder, so we are collaborating with the radiology department there. They do lots of scan, which are non-gallbladder also, which have normal gallbladder. When the gallbladder cancer is there, of course, the patient would have come with some complaint. Okay, so the gallbladder cancer without complaint, that data we do not have. In the context of medical imaging, there is a word for it, which we call the screening setting and diagnostic setting. So we do not have the data of the gallbladder cancer in the screening setting. Okay, when the gallbladder cancer may have been very small and the patient did not have any complaints of the data. So in that case, the model could have been biased. On the other hand, luckily, we have the data in the breast cancer setting. So the PGI Chandigarh, few years back, actually created this bus where there was a mammography machine, and they sort of took it around in the villages of Punjab, and they gave us about 4,000 images, of which I think, if I'm right, about 300 were positives. So we have breast cancer data which is in the screening setting, because right now you don't know, you're just going to the villages, and some you happen to get them. That situation is not yet there in the GBV.
Provide a small token of appreciation for the speaker.
No, thank you.